Picture the universe not as the vast, glittering expanse we know today, but as an endless sea of darkness, a silent, formless void where not a single star had yet flickered to life. Now imagine a moment so transformative, it reshaped everything. What if the cosmos experienced a second Big Bang, not an explosion of matter this time, but a dazzling rebirth of light? This isn't science fiction, it's the story of the Cosmic Reionization Era, one of the greatest unsolved mysteries in the history of our universe, a time when the first stars and galaxies pierced the primordial fog, flooding space with radiation so powerful, it tore apart the very fabric of the cosmos. And here's the wildest part, we're still piecing together how it happened. Think of this as the ultimate cosmic detective story. The clues are scattered across billions of light-years ancient light captured by our most powerful telescopes, whispers from the dawn of time. But the deeper we look, the more questions we uncover. How did those first stars, born in the crushing depths of darkness, manage to illuminate the entire universe? What forces drove this epic transformation, and why did it take hundreds of millions of years to unfold? This isn't just about distant galaxies, it's about our origins. Every atom in your body, every speck of stardust around you, traces back to this pivotal chapter. So let's embark on a journey, one that takes us to the edge of what we know and beyond. We'll unravel 25 of the most baffling mysteries from this era, from the enigma of the first supermassive black holes to the shocking discovery of galaxies that defied all expectations. Along the way, you'll witness the universe as it awakened from its ancient slumber, forging the conditions that made life possible. By the end, you won't just understand the Cosmic Reionization Era, you'll feel it. The drama, the chaos, the sheer scale of a transformation that shaped everything we see today. Ready to step into the unknown, the cosmos is waiting. The Cosmic Reionization Era didn't just happen, it was set into motion by something extraordinary, something powerful enough to tear apart the very atoms filling the early universe. But what exactly flipped the switch? For decades, astronomers have wrestled with this first great mystery. What triggered reionization in the first place? The answer isn't simple, because the ancient universe played its cards close to its chest. One leading theory points to the first generation of stars, unimaginably massive and blazing with ultraviolet light. These weren't the familiar, steady burning stars of today, they were titans, hundreds of times heavier than our Sun, living fast and dying young in spectacular supernova. Their intense radiation could have stripped electrons from hydrogen atoms, turning the foggy primordial universe transparent. But here's the catch, there might not have been enough of them to do the job alone. Then there's the wildcard quasars, powered by ravenous supermassive black holes feasting on gas in the hearts of early galaxies. These cosmic powerhouses pump out enough energy to outshine entire galaxies, and their radiation is more than capable of ionizing hydrogen. But did they emerge early enough to light up the universe, or were they too rare, too late to be the main culprit? Now the James Webb Space Telescope is flipping the script. Its infrared eyes peer deeper into the past than ever before, revealing galaxies brighter and more active than anyone predicted. Some of these ancient systems were already forming stars at a ferocious rate, challenging our assumptions about how quickly reionization could have started. Others may have harbored black holes larger than expected, adding fuel to the quasar debate. The truth might be even messier, a chaotic collaboration between stars, black holes, and forces we haven't yet uncovered. Whatever the case, one thing's certain, the trigger of reionization wasn't just a single event, it was a cosmic revolution, and we're only beginning to trace its origins. If the Cosmic Reionization Era was a cosmic revolution, then its timeline is the ultimate cold case, one where the evidence keeps contradicting itself. Pinpointing when this grand transformation started and ended should be straightforward, right? Not even close. depending on where astronomers look, the universe seems to be telling two very different stories. Take the cosmic microwave background, that faint glow from the infancy of the cosmos. Its subtle imprints suggest reionization was a slow burn, starting around redshift 20 and stretching over hundreds of millions of years. But then there are quasars, beacons of light from the early universe, whose absorption lines paint a radically different picture. Their light reveals forests of hydrogen atoms that seem to have been ionized much earlier, hinting at a faster, more dramatic process. Why the discrepancy? The answer might lie in one of the most fascinating wrinkles of this era. Reionization wasn't uniform. Imagine lighting a candle in a pitch-black room, then another, and another, each flame carving out its own little bubble of light, slowly merging until the whole space is illuminated. That's patchy reionization in action. Some regions of the universe, packed with early galaxies and quasars, could have been ionized far sooner than others, where stars were slower to ignite. This cosmic unevenness means our measurements depend entirely on where we're looking and what we're measuring. Even the James Webb Space Telescope, our most powerful time machine, is adding to the intrigue. Some of its deep field images show fully formed galaxies much earlier than expected, suggesting the timeline might need another rewrite. Could reionization have started in scattered pockets, only to accelerate in a sudden cascade? Or was it a stop-and-start affair, with periods of intense ionization followed by lulls? Every new discovery seems to deepen the mystery rather than solve it. One thing's clear, the universe didn't flip a switch. It flickered sporadically, unpredictably, and we're only beginning to map the shadows it left behind. Dark matter, the universe's most elusive architect, may have played a hidden role in the Cosmic Reionization era, pulling strings from the shadows. While it never directly emitted a single photon, its gravitational influence could have been the silent orchestrator behind the scenes, shaping where and when stars ignited, and ultimately, how light broke free. Think of dark matter as the scaffolding of the cosmos. Its invisible tendrils formed vast webs, drawing ordinary matter into dense knots where galaxies could take shape. Without this gravitational blueprint, the first stars might have been scattered too thin to ionize the universe effectively, but simulations reveal something astonishing. Dark matter didn't just create galaxies, it sculpted them into the perfect engines of reionization. In regions where dark matter clustered most densely, galaxies formed earlier and burned brighter, spewing ultraviolet radiation that carved out sprawling ionized bubbles. These weren't random, they followed the hidden patterns of dark matter's cosmic web. Here's where it gets even stranger. Some models suggest dark matter's behavior, whether it was cold, warm, or something even more exotic, could have dramatically altered reionization's pace. Cold dark matter, moving sluggishly, would have clumped quickly, creating dense galaxy hubs that lit up fast. Warm dark matter, more energetic and diffuse, might have delayed galaxy formation, stretching reionization over a longer timeline. The truth could lie somewhere in between, with dark matter's properties leaving subtle fingerprints in the way ionized bubbles grew and merged. Yet the James Webb Space Telescope is complicating the picture again. Some of the earliest galaxies it spotted appear smaller and fainter than dark matter simulations predicted. Could dark matter have distributed itself differently than we thought? Or are we seeing the fallout of an even deeper mystery, like interactions between dark matter and early cosmic radiation? One thing's certain, dark matter didn't just watch from the sidelines. It set the stage, determining where the first stars would blaze, how quickly their light would spread, and even how long the universe's great awakening would take. Unraveling its role isn't just about understanding reionization, it's about decoding the invisible framework that shaped everything we see today. Among the biggest surprises from the Cosmic Reionization era is something that isn't there: the dwarf galaxies that should have been everywhere. According to our best simulations, the early universe ought to have been teeming with these small, faint galaxies. each contributing their share of ultraviolet light to reionization. But when astronomers actually went looking, they found a cosmic desert, far fewer dwarfs than expected. This isn't just a census problem, it's a full-blown paradox that shakes our understanding of how the first structures formed. Here's what makes this mystery so frustrating. Dwarf galaxies are like the worker bees of cosmic reionization, small but numerous. Their combined radiation should have been crucial for stripping electrons from hydrogen atoms. Computer models based on dark matter theory predicted thousands of them lurking around larger galaxies, yet observations show only a fraction of that number. Somewhere between our simulations and reality, an entire population of cosmic pioneers has gone missing. Part of the answer might lie in a phenomenon called feedback, the self-destructive tendencies of early galaxies. Imagine a dwarf galaxy forming in the primordial universe. Its first massive stars explode as supernova, blasting away the gas needed to make new stars. Without fresh fuel, the galaxy essentially shuts down, fading into obscurity before telescopes can spot it. This could explain why we don't see as many dwarfs as we should. They burned out too quickly. But there's a twist. If feedback were the sole culprit, we'd expect to find some remnants of these galaxies, dim, gas-poor ghosts lurking in the cosmic background. Instead, even our most sensitive instruments struggle to detect them. That's led to another radical idea. What if dark matter isn't behaving the way we thought? Most simulations assume cold dark matter, which clumps easily into small halos perfect for dwarf galaxies. But if dark matter were slightly warmer, more energetic, those tiny halos might never form, leaving us with a universe where dwarf galaxies are rare by design. The plot thickens with the James Webb Space Telescope's latest discoveries. Some of the smallest galaxies it spotted in the early universe are far brighter and more massive than expected, adding yet another puzzle. These galaxies aren't just outliers, they're rewriting the rules, challenging our assumptions about how structure forms in the first place. Could there have been an unexpected interplay between dark matter and baryonic matter that favored larger galaxies, or did some environmental factor, like cosmic radiation, suppress dwarf formation entirely? Every missing dwarf galaxy is a silent witness to forces we're only beginning to understand. Their absence doesn't just leave gaps in our maps, it forces us to reconsider the fundamental physics that built the universe. And until we solve this mystery, our picture of cosmic dawn will remain frustratingly incomplete. Consider the light from a distant quasar as a cosmic message in a bottle, a beam that's traveled billions of years before reaching us, carrying secrets from the infancy of the universe. When astronomers split this light into its spectral components, they uncover something extraordinary, a forest of dark absorption lines, each one a fingerprint left by hydrogen atoms that once stood in the quasar's path. This is the Lyman-alpha forest, and it might be the closest thing we have to a time machine for studying reionization, but the story it tells isn't clean or straightforward. It's riddled with anomalies that defy explanation. These absorption lines act like a cosmic barcode, revealing how much neutral hydrogen with its electrons still attached existed at different points in the universe's history. In theory, as reionization progressed, the forest should thin out, with fewer lines indicating less neutral hydrogen blocking the quasar's light, but observations reveal wild fluctuations. Some regions show nearly complete ionization, as if a spotlight had swept through, while others remain stubbornly opaque, like patches of primordial fog that refuse to burn away. Why would the universe clean up some areas so efficiently while leaving others untouched? One clue lies in the spacing of these lines. Closely packed lines suggest dense pockets of hydrogen, while wider gaps hint at ionized bubbles. But the patterns don't match simulations. Some quasars reveal forests that are sparse where they should be dense, or vice versa, as if the universe skipped steps in its reionization playbook. Even more puzzling, the opacity of these hydrogen clouds doesn't always align with the expected timeline. Some appear too transparent for their era, as if something or someone had already stripped their electrons ahead of schedule. Could this variability mean reionization wasn't just patchy, but chaotic? Imagine a wildfire spreading unevenly, leaping over some areas while consuming others completely. Perhaps quasars or unusually bright galaxies ionized their surroundings early, creating vast bubbles that later merged, or maybe dark matter's distribution played a role, with hydrogen clumping unpredictably in its gravitational wake. Then there's the temperature factor. Hydrogen absorbs light differently depending on how hot or cold it is. If some regions were heated earlier by the first supernova or black hole jets, their absorption signatures would weaken, mimicking the effects of ionization. This could explain why parts of the forest appear more transparent than they should, but it raises another question: what caused this heating, and why wasn't it uniform? The James Webb Space Telescope is now adding fuel to the fire. Its observations of early galaxies suggest star formation could have been even more explosive than we thought, with bursts of radiation punching holes in the hydrogen fog at irregular intervals. Meanwhile, other studies hint that cosmic rays or dark matter interactions might have contributed to the uneven ionization. The truth is, every quasar's forest tells a slightly different story, and no single model can explain them all. These anomalies aren't just gaps in our data, they're windows into the messy, unpredictable nature of cosmic dawn, and until we untangle them, the Lyman-alpha forest will remain one of reionization's most tantalizing puzzles. The first stars weren't just luminous, they were cosmic alchemists, forging the elements that would later seed planets and life itself. But these pioneers, known as population 3 stars, remain one of reionization's most haunting mysteries. Unlike modern stars, they were born in a universe devoid of metals elements heavier than hydrogen and helium, making them unimaginably massive, scorching hot, and blindingly bright. Their spectra, the unique fingerprints of their light, should be unmistakable, yet despite decades of searching, not a single pristine population 3 star has been conclusively observed. Why? The answer lies in the brutal physics of their existence. These stars lived fast and died young, with lifetimes measured in mere millions of years. Their ultraviolet radiation was so intense, it could ionize hydrogen across vast distances, but their brilliance came at a cost. The largest ones likely collapsed directly into black holes, leaving no stellar corpses to study. Others detonated as supernovae so violent, they scattered the first heavy metals into the cosmos, contaminating later generations of stars and erasing the pristine conditions of their birth. To find a population 3 star today would be like spotting a single, unblemished snowflake in a blizzard, nearly impossible, but astronomers haven't given up. The James Webb Space Telescope is hunting for indirect clues, like the ghostly afterglow of their deaths. When these stars exploded, their supernova would have left behind distinct chemical signatures, odd ratios of elements like carbon, oxygen, and silicon, forged in their cores under extreme conditions. Some models even predict a rare type of explosion called a pair instability supernova, a runaway thermonuclear detonation so powerful it vaporizes the entire star, leaving no remnant behind. These events would outshine entire galaxies, and their light, redshifted over billions of years, might finally be within Webb's reach. The challenge: distinguishing these ancient fireworks from later supernova, without metals to act as cosmic coolants. Population 3 stars burned at temperatures far exceeding modern stars, producing unusual elements like ionized helium in their spectra. If Webb catches a supernova with these exotic fingerprints, it could confirm the existence of these elusive giants. But there's another twist. Some theorists suggest the first stars might not have been solitary behemoths. Instead, they could have formed in tight clusters, their combined light ionizing the universe in unison. This would make their individual spectra even harder to isolate, like picking out a single voice in a celestial choir. The stakes couldn't be higher. Population 3 stars weren't just the engines of reionization, they were the universe's first factories, synthesizing the raw materials for everything that followed. Finding them or even their remnants would unlock secrets about how the cosmos transitioned from darkness to light. Until then, their spectra remain a tantalizing cipher, written in wavelengths we're only beginning to decode. Quasars should have been the ultimate cosmic powerhouses, capable of ionizing vast swaths of the early universe with their blistering radiation. But here's the problem: when you crunch the numbers, something doesn't add up. These brilliant beacons, fueled by supermassive black holes guzzling gas at unbelievable rates, were staggeringly bright. A single quasar could outshine an entire galaxy, its ultraviolet fury stripping electrons from hydrogen atoms like a cosmic sandblaster. Yet for all their might, quasars faced a critical limitation: time. Most quasars flared violently for just a few million years before running out of fuel or choking on their own radiation. Reionization, on the other hand, dragged on for hundreds of millions of years. It's like trying to light up a dense, endless forest with a handful of flashlights flickering on and off at random. Even if every quasar worked overtime, their combined efforts might not have been enough to pierce the universe's primordial gloom. So were these cosmic lighthouses truly the driving force behind reionization, or just spectacular side characters in a much larger drama? Enter the light bulb in a fog analogy. Imagine switching on a lamp in a thick mist. The light only penetrates so far before the fog scatters it into useless haze. Quasars faced a similar challenge. Their radiation could carve out ionized bubbles around them, but those bubbles had limits. Beyond a certain radius, the relentless hydrogen fog reasserted itself, swallowing the light whole. For quasars to have single-handedly ionized the cosmos, they'd need to be packed together nearly shoulder to shoulder, their overlapping bubbles leaving no neutral hydrogen untouched. But the early universe wasn't that crowded. Recent observations from the James Webb Space Telescope deepened the puzzle. While quasars were indeed luminous, they appear to have been rarer in the reionization era than once thought. Some models suggest their activity might have peaked too late, after the bulk of ionization was already underway. Others propose that quasars primarily lit up regions already seeded by galaxies, like torches passed between cosmic neighbors rather than solitary firestarters. Then there's the black hole paradox. To power a quasar, you need a supermassive black hole, but how did these monsters grow so massive so quickly? Some could have formed from the direct collapse of primordial gas clouds, skipping the usual star phase entirely. Others might have gorged themselves in brief, violent feeding frenzies. Either way, their very existence challenges our understanding of black hole infancy, adding another layer to the quasar conundrum. Perhaps the most tantalizing clue lies in their leftovers. When quasars fade, their ionized bubbles don't instantly collapse. These ghostly regions linger, overlapping with others to create a patchwork of transparency. Over time, the cumulative effect of countless short-lived quasars might have tipped the scales, amplifying the work of stars and galaxies. The verdict: quasars were likely key players but not solo acts. Their dazzling bursts added crucial momentum to reionization, punching holes in the hydrogen fog that other sources could expand. Together they formed a cosmic relay race, passing the baton of ionization across generations until the entire universe blazed with light. Hydrogen, the simplest and most abundant element in the early universe, held the key to reionization, but it didn't play fair. Instead of spreading out smoothly like butter on cosmic toast, it clumped together in a chaotic patchwork of dense clouds and near-empty voids. This uneven distribution turned reionization into a tug-of-war, with some regions surrendering their electrons easily while others clung stubbornly to neutrality. The result: a bizarre cosmic battleground where light advanced in fits and starts, leaving behind fossilized pockets of hydrogen that resisted ionization for millions of years longer than their surroundings. Simulations reveal just how dramatic this unevenness was. Picture a sponge, some parts soaked with water, others bone dry. In the densest knots of hydrogen, ultraviolet radiation from early stars and quasars faced a grueling marathon. Each photon had to rip through layer after layer of atoms, losing energy along the way, until the radiation grew too weak to ionize further. These thickets became cosmic holdouts, islands of primordial fog in an otherwise transparent sea. Meanwhile, in sparser regions, light raced ahead almost unimpeded, creating vast bubbles of ionized gas that expanded like wildfire. But why did these dense regions put up such a fight? It all comes down to physics. Hydrogen atoms in crowded environments constantly collide, exciting one another and making it harder for radiation to strip their electrons. It's like trying to melt a glacier with a hairdryer, possible, but painfully slow. Worse, the first ionizing photons didn't just have to break individual atoms, they had to overcome a domino effect. Neutral hydrogen absorbs photons at specific wavelengths, so once the easiest targets were ionized, the remaining atoms required even higher energy radiation to dislodge. This created a bottleneck, with denser regions demanding absurd amounts of energy to fully clear. The James Webb Space Telescope has spotted eerie echoes of this struggle. Distant quasars shining through ancient gas reveal surprising shadow zones, stretches of space where neutral hydrogen lingered long after surrounding areas had been ionized. These cosmic relics shouldn't exist if reionization were uniform, yet there they are, defying expectations. Some theories suggest these holdouts sheltered near massive galaxy clusters, where ultraviolet radiation couldn't penetrate the thick gas swirling around them. Others propose they mark regions where dark matter's gravitational pull trapped hydrogen in deep, radiation-proof wells. The real twist: these neutral fossils might hold clues to an even deeper mystery. If hydrogen clumped more intensely in certain areas, it could mean the primordial universe wasn't as smooth as we've assumed. Tiny quantum fluctuations from the Big Bang might have amplified into wild density contrasts, setting the stage for reionization's uneven march. Or perhaps early magnetic fields, still poorly understood, funneled gas into dense ribbons that stymied radiation. One thing's certain: hydrogen didn't just passively accept its fate. Its clumps and voids dictated where light triumphed and where darkness endured, weaving a tapestry of ionization so complex, we're still deciphering its patterns billions of years later. If the universe had a birth certificate, its official time of arrival would read 380,000 years after the Big Bang, the moment atoms formed and light broke free. But what happened next feels like cosmic procrastination on an epic scale. Why did the universe wait another 100 million years before sparking its first stars? This gap, known as the cosmic dawn's delay, isn't just idle time, it's a cliffhanger in the story of creation, one where the laws of physics themselves seem to hesitate. At first glance, the ingredients for starbirth were all there: vast clouds of hydrogen and helium, gravity's relentless pull, and the cosmic microwave background providing a faint afterglow of warmth. Yet stars didn't ignite. The hitch: temperature. The early universe was lukewarm, too warm for gas to collapse efficiently. Without a way to shed heat, those primordial clouds couldn't condense into dense enough knots to trigger nuclear fusion. It's like trying to form ice cubes in a room that's just slightly too warm. No matter how much water you gather, nothing solidifies. Enter molecular hydrogen, the unsung hero or villain of this delay. Unlike familiar H2 molecules today, these early versions acted as the universe's first coolant. When hydrogen atoms paired up, they gained a quirk: the ability to vibrate and release heat as infrared radiation. This subtle energy dump allowed gas clouds to shrink ever so slightly, inching toward the density needed for star formation. But here's the catch: molecular hydrogen was absurdly finicky to make. Without heavy elements or dust grains to help atoms bond, It formed at a glacial pace through rare three-atom collisions. Talk about a cosmic bottleneck. Then there's the chicken and egg twist. Modern stars form easily because they inherit heavy elements from previous generations, elements that act like microscopic radiators, helping gas clouds cool rapidly. But the first stars had no such luxury. They needed to bootstrap themselves into existence using only hydrogen and helium, like building a skyscraper with nothing but toothpicks and glue. The result, a painfully slow dance of trial and error, with gas clumping, warming, and fizzling out over millions of years until finally, a handful of clouds crossed the density threshold. Dark matter played its part too. Its gravitational pull helped gather gas into protogalactic halos, but even these dark matter cradles couldn't speed things up without efficient cooling. Simulations show halos needed to reach a critical mass about 1 million times the Sun's weight before their gas could collapse. Until then, the universe was stuck in a holding pattern, its star-making factories idling in neutral. The James Webb Space Telescope is now uncovering clues about this awkward adolescence. Some of the earliest galaxies it spotted appear to have formed stars in sudden bursts, suggesting that once cooling mechanisms finally kicked in, star birth wasn't just slow and steady, it was explosive. Other observations hint at pockets of the cosmos where conditions were just right earlier than expected, like cosmic microwave hotspots that gave gas clouds a head start. This delay wasn't a bug in the universe's code, it was a feature. That 100-million-year wait ensured the first stars were monstrously massive, blazing hot enough to ionize the cosmos. Had they formed earlier, they might have been smaller, dimmer, and utterly incapable of lighting up the universe. So while the cosmic dawn's lag might seem like a plot hole, it's actually the reason we're here at all. Without it, the night sky might still be dark. Imagine a cosmic balancing act where the very force driving reionization, the blazing ultraviolet light of early stars, also sabotaged its own progress. This is the reionization feedback loop, a paradoxical dance of creation and destruction that might hold the key to why the universe took so long to wake up. When those first monstrous stars ignited, their radiation didn't just ionize hydrogen, it fundamentally altered the rules of star formation. Ultraviolet photons ripped electrons from atoms, but they also carried enough energy to heat surrounding gas, preventing it from cooling and collapsing into new stars. It's like trying to light a campfire during a hurricane. The same energy that sparks flames also scatters the kindling. The result, a self-regulating universe, where each burst of star formation sowed the seeds of its own slowdown. This feedback wasn't just a minor hiccup, it was a cosmic throttle. Simulations show that in regions where early stars lit up intensely, their radiation heated vast bubbles of gas to temperatures exceeding 10,000 degrees. Hot gas resists compression, so while these bubbles became ionized quickly, they also became star-forming dead zones. New stars could only ignite at the edges where the radiation hadn't yet reached, or in shielded pockets deep inside dense clouds. This stop-and-start process could explain why reionization didn't happen in a single, explosive flash, but as a slow, sputtering emergence of light. But here's where it gets even more fascinating. Some models suggest this feedback wasn't uniform. Smaller galaxies with weaker gravity were especially vulnerable. A handful of massive stars could heat their host galaxy's entire gas supply, shutting down star formation entirely until fresh gas drifted in from intergalactic space. Larger galaxies, though, had enough gravity to hold onto their gas, allowing star formation to persist despite the radiation onslaught. This might explain another puzzle: why some corners of the universe reionized earlier than others. Regions dominated by small, fragile galaxies would have experienced fits and starts, while areas with massive galaxies became steady lighthouses, ionizing their surroundings more efficiently. The James Webb Space Telescope has spotted echoes of this tug-of-war in ancient galaxies. Some show abrupt gaps in their star-forming history, periods of furious activity followed by eerie quiet, as if their gas reserves had been temporarily sterilized by radiation. Others reveal oddly distributed stellar populations, with stars clustered in rings or outskirts, avoiding the radiation-blasted cores. These aren't just quirks, they're fossilized evidence of feedback in action. Yet the feedback loop might have had an unexpected accomplice, supernova. When those first stars died, their explosive deaths injected even more energy into the gas, further heating it and spreading heavy elements that changed how future generations of stars formed. These metals acted like cosmic antifreeze, helping gas cool more efficiently, but only after the initial feedback had already done its damage. It's a classic case of short-term pain for long-term gain. The same processes that delayed reionization also set the stage for the universe we know today. So is this feedback loop a flaw in the cosmic design? Far from it. Without it, the universe might have burned through its gas too quickly, creating a fleeting era of brilliant but unsustainable starlight. Instead, feedback forced the cosmos to ration its star-forming fuel, stretching reionization into a gradual crescendo rather than a fleeting firework. The result, a universe that took its time so that light, and eventually life, could find their footing. While hydrogen reionization steals the spotlight, there's a second cosmic revolution that's often overlooked: the reionization of helium. Unlike hydrogen, which lost its electrons to starlight, helium required an even more brutal assault. Its electrons are bound tighter, demanding ultraviolet radiation so extreme, only the universe's most violent engines could tear them free: quasars. This marked helium's second ionization, a hidden chapter that reshaped the cosmos yet again, leaving ghostly imprints we're still deciphering today. The plot twist. Helium didn't just sit idle during hydrogen reionization. It was ionized once already, back when the universe was just 380,000 years old, only to regain its electrons as everything cooled. But later, when quasars emerged, their blistering radiation packing 50 times more energy than typical starlight, stripped those electrons away for good. This double ionization created a cosmic fingerprint that's proving devilishly hard to read. The big question: did helium and hydrogen reionization happen side by side, or was helium's reckoning delayed? Clues hide in the cosmic microwave background. Photons from this ancient light bear subtle scars from their journey through ionized gas, while hydrogen reionization left a clear mark, a dip in the CMB's polarization. Helium's contribution is fainter, mudded by overlapping signals. Some models suggest helium reionization occurred around redshift 3, long after hydrogen's fog had lifted. Others argue quasars fired up early enough to make both processes overlap, turning the universe into a multi-layered battleground where two elements were ionized at once. Then there's the temperature problem. Ionizing helium doesn't just free electrons, it supercharges them, heating intergalactic gas to temperatures exceeding 20,000 degrees. This feverish aftermath should distort the Lyman-alpha forest, the telltale absorption lines in quasar light. Yet when astronomers measure these distortions, the results are bafflingly inconsistent. Some regions show evidence of helium's searing touch, while others appear oddly cool, as if quasars missed entire swaths of the cosmos. The James Webb Space Telescope is now peeling back the layers. By studying quasars at the exact epoch when helium reionization should have peaked, it's revealing a patchwork process: some bubbles ionized to perfection, others stubbornly neutral. This irregularity suggests quasars didn't just flip a switch, they flickered unevenly, their radiation carving tunnels through the helium fog rather than flooding it all at once. The deeper implications are staggering. If helium reionization indeed lagged behind hydrogen's, it means the universe endured two distinct waves of transformation, first a starlit dawn, then a quasar-driven noon. But if they overlapped, our models of cosmic evolution need a rewrite. One thing's certain: helium's silent upheaval wasn't just a footnote, It was a second act in the universe's Great Awakening, and its echoes still shape the cosmos we see today. Of all the cosmic echoes we expected to hear from the reionization era, the 21-centimeter signal was supposed to be unmistakable, a faint but persistent whisper from neutral hydrogen atoms across the universe. Yet when radio telescopes finally tuned into this primordial frequency, they encountered something far more puzzling: silence, not the empty hush of a universe untouched by light, but an eerie absence where a chorus should have been. This missing signal isn't just a technical glitch, it's a cosmic detective story with stakes that could rewrite our understanding of dark matter, early stars, and the fundamental laws of physics. The 21-centimeter line arises from a quirk of hydrogen physics. When the spin of an atom's electron flips relative to its proton, it releases or absorbs a photon with a wavelength of 21 centimeters, a radio fingerprint detectable across interstellar space. During reionization, this signal should have morphed in predictable ways, first as a deep absorption trough when cold hydrogen absorbed cosmic microwave background photons, then as emission once ultraviolet light heated the gas. But the absorption signal detected by experiments like EDGES was shockingly strong, twice as deep as models predicted, while later attempts to catch the emission phase found bafflingly little. It's like hearing a thunderclap but no rain, or spotting footprints that vanish mid-stride. Foreground interference is the obvious suspect. Our own galaxy's radio chatter, synchrotron radiation from cosmic rays spiraling in magnetic fields, could be drowning out the signal. Yet meticulous filtering hasn't resolved the discrepancy. This leaves two unsettling possibilities: either our models of early hydrogen are catastrophically wrong, or something entirely unexpected was at work. One radical theory points to dark matter. If certain hypothetical particles interacted with hydrogen atoms, they could have siphoned away energy, cooling the gas to temperatures far below what standard physics allows. This ultra-chilled hydrogen would absorb background photons more aggressively, explaining the EDGES trough, but it demands dark matter with properties beyond anything we've imagined. Another twist comes from the timing of the signal's disappearance. If the 21-centimeter line faded too early, it might mean the first stars heated the universe faster than simulations suggest. Some primordial galaxies could have been wildly efficient radiators, their ultraviolet light flooding space before their numbers alone would predict. Alternatively, cosmic rays from early supernova might have peppered hydrogen with extra energy, scrambling the spin states needed to produce the signal. The plot thickened when the Hera telescope array failed to detect the expected emission signal at all. This silence implies that by the time reionization peaked, hydrogen was either too ionized or too hot to produce much 21-centimeter radiation, but that contradicts other evidence suggesting neutral pockets persisted far longer. Could there have been a second, later wave of cooling, or does the answer lie in the complex interplay between galaxies and their surroundings, where ultraviolet light and cosmic rays danced in feedback loops we're only beginning to map? Every failed detection deepens the mystery. The 21-centimeter signal isn't just missing, it's missing unevenly, with gaps that defy uniform explanations. Like static on a radio dial, these anomalies might be hiding a message that the cosmic dawn was stranger, wilder, and more beautiful than we ever dreamed. Until we crack its code, this silence remains one of reionization's most profound puzzles, a cosmic whisper we're still learning to hear. Galaxies today collide in slow, majestic dances, spirals merging over billions of years with bursts of new stars sprinkled like cosmic glitter. But rewind to the Cosmic Reionization Era, and these encounters were anything but graceful. Imagine two firestorms crashing headlong into each other, spewing ultraviolet radiation as their gas clouds compressed in violent shockwaves. These chaotic mergers might have been reionization's hidden accelerants, supercharging star formation and flooding the universe with ionizing light faster than solitary galaxies ever could. Yet simulations and observations are locked in a tug-of-war over just how pivotal these collisions truly were. Most cosmological models downplay mergers during reionization, treating them as background noise. After all, the early universe was far emptier than today, making galactic smash-ups relatively rare, but rarity doesn't equal insignificance. When mergers did occur, their impact could have been explosive. Gas crush between colliding galaxies ignites starbursts, episodes where stars form hundreds of times faster than normal. Each burst would have unleashed a torrent of ultraviolet photons, punching holes in the hydrogen fog far larger than a single galaxy could manage alone. Think of it like striking flint. A lone spark might sputter, but slam two rocks together and you get a firestorm. The James Webb Space Telescope has thrown gasoline on this debate. Its deep field images reveal galaxies from the reionization epoch with bizarre, distorted shapes, tadpole tails, warped disks, and even chains of stellar clumps that look less like unified galaxies and more like cosmic car crashes frozen in time. Some show signs of multiple dense cores, as if several smaller galaxies were caught mid-collision. Others are surrounded by sprawling halos of young stars, the telltale aftermath of merger-driven starbursts. These aren't the serene spirals of later eras, they're train wrecks of star formation, and their radiation output could dwarf that of their quieter neighbors. Yet simulations struggle to replicate this chaos. When researchers model the early universe, mergers often appear too brief or too gas-poor to drive sustained starbursts. Part of the disconnect might lie in resolution. Many simulations can't capture the fine-scale turbulence where gas collapses into stars during a collision. It's like trying to predict the shape of a snowflake by only tracking the storm clouds. Another wrinkle: the primordial gas fueling these mergers lacked heavy elements, making it harder to cool and fragment into stars. Without metals to act as cosmic coolant, mergers might have fizzled more often than they flared. But what if we're missing a key ingredient? Dark matter halos, invisible and pervasive, could have turned mergers into reionization powerhouses. When two halos merged, their combined gravity might have funneled gas into dense, unstable reservoirs, creating perfect conditions for runaway star formation. Some theorists even propose that dark matter interactions, still poorly understood, could have heated or compressed gas in ways that amplified starbursts. The wild card: magnetic fields. If early galaxies wove strong magnetic nets during collisions, those fields might have channeled gas into star-forming filaments more efficiently than gravity alone. The stakes here are cosmic. If mergers were indeed reionization's secret weapon, then our models of how light conquered the universe need a rewrite. Instead of a steady march of ionization, we might be looking at a punctuated equilibrium, long lulls broken by violent leaps forward whenever galaxies collided. This wouldn't just change our timeline, it would reshuffle the entire cast of cosmic heroes, putting galaxy mergers center stage alongside quasars and massive stars. The deeper we look, the clearer it becomes. The early universe didn't play by neat, predictable rules. Its galaxies didn't just grow, they clashed, cannibalized, and lit up the darkness in fits and starts. And somewhere in that chaos lies the answer to one of reionization's most explosive mysteries. The first supernova didn't just light up the cosmos, they poisoned it. In their dying moments, these massive stars forged heavy elements like carbon, oxygen, and iron, then blasted them into the void. This cosmic contamination, what astronomers call metal pollution, should have been a disaster for star formation. After all, pristine gas collapses more easily into stars, so logic says adding metals would stifle the process. Yet the opposite happened. Instead of slowing down, star formation kicked into high gear, creating a paradox that might hold the key to reionization's ultimate success. Metals acted as cosmic refrigerants. In the early universe, gas clouds had no efficient way to cool. Without heavy elements to radiate away heat, collapsing hydrogen just bounced back like a rubber ball, resisting compression. But when supernova seeded space with metals, everything changed. These impurities absorbed energy and re-emitted it as infrared light, allowing gas to shed heat and crumple into denser knots. Suddenly, smaller clouds could reach the critical density needed for star birth clouds that would have stayed diffuse forever in a metal-free universe. It's like adding ice cubes to a scorching drink. The extra cooling accelerates condensation, forming new droplets where none could exist before. But here's the twist: this cooling effect wasn't uniform. In regions drenched by multiple supernova, metals may have worked too well. Gas cooled so rapidly it fragmented into tiny clumps, spawning swarms of puny stars instead of the massive, ionizing giants reionization required. Imagine trying to heat a room with birthday candles instead of a bonfire. It's possible, but painfully inefficient. This could explain why some corners of the early universe lagged behind in ionization, their star formation diverted into countless dim embers rather than a few blazing beacons. Meanwhile, in areas with just a sprinkle of metals, the balance was perfect. Gas cooled enough to form stars efficiently, but retained enough heat to avoid over-fragmenting. These regions became reionization's powerhouses, producing both massive stars and the smaller ones that followed. The result, a self-sustaining cycle. Supernova polluted the gas, which cooled and formed more stars, which exploded and polluted further, each generation spreading metals and ionizing radiation wider than the last. The James Webb Space Telescope has spotted echoes of this feedback loop in action. Some ancient galaxies show bizarre chemical fingerprints, pockets of gas rich in oxygen, but lacking heavier elements like iron. This suggests early supernova didn't mix their metals evenly, leaving some gas pristine while oversaturating others. These uneven conditions could have created a patchwork of star-forming efficiency, explaining why reionization advanced in fits and starts. Yet the paradox goes deeper. Metals didn't just aid cooling, they changed how stars lived and died. The first stars, born from pure hydrogen and helium, burned ferociously and died young. But metal-polluted stars, they could afford to be smaller, steadier, and longer-lived. This shift might have extended reionization's timeline, trading brief, intense bursts of ionization for a slower, more sustained campaign. So did metal pollution speed up reionization or drag it out? The answer might be both. Early on, metals turbocharged star formation, flooding the universe with ionizing photons. But over time they may have throttled back, favoring smaller stars that kept the lights on longer but burned less brightly. It's a reminder that the cosmos rarely follows simple rules. Sometimes, pollution isn't just a byproduct of progress. It's the engine. The cosmic web isn't just the universe's skeleton, it was reionization's hidden highway, a sprawling network of filaments that channeled light like fiber optic cables threading through the darkness. While we often picture reionization as a uniform wave sweeping across space, the reality was messier, more beautiful, and deeply tied to this intricate architecture. Ionizing radiation didn't spread outward in neat spheres. It raced along the cosmic web's dense filaments, leaving vast voids as the last holdouts of primordial fog. The result, a universe where light didn't conquer the darkness, it flowed through its veins. Simulations reveal this process with stunning clarity. Imagine pouring water onto a sponge. Instead of soaking evenly, the liquid follows the sponge's fibrous structure, seeping quickly along interconnected channels while bypassing hollow pockets. Reionization worked the same way. Galaxies nestled in filaments, packed close like pearls on a string, blasted ultraviolet light down these cosmic corridors. Their radiation traveled farther and faster here, ionizing hydrogen in dense ribbons while struggling to penetrate the emptiness of voids. Over time, these ionized filaments merged, creating a labyrinth of transparency, but the voids, isolated and star-poor, resisted until the very end. Why did light favor filaments? Gravity's cruel efficiency is to blame. Dark matter's pull dragged gas into these thread-like structures early on, creating rivers of raw star fuel. Where filaments cross, galaxies clustered, their combined radiation turning intersections into blazing hubs of ionization, yet voids, bereft of such scaffolding, remained cosmic backwaters. With fewer galaxies to ignite reionization, their hydrogen lingered in darkness, like shadowed valleys between mountain ranges catching the first sunrise. The James Webb Space Telescope has given us ghostly glimpses of this web in action. Distant quasars backlighting ancient gas reveal ionized tunnel stretches where filaments once glowed with ultraviolet light, now traced by eerie absences in hydrogen absorption. Other observations show voids with stubbornly neutral gas, their isolation preserving whispers of the universe's darker days. These aren't random anomalies, they're fossils of a cosmic watershed where the flow of light was dictated by geography. But here's the twist: the cosmic web didn't just guide reionization, it accelerated it. Radiation traveling along filaments could leapfrog between galaxies, like fire hopping between closely spaced trees. Each new galaxy added to the chain became a relay station, amplifying the signal. Meanwhile, voids acted as barriers, their emptiness forcing light to take detours. This uneven terrain explains why reionization's timeline varies so dramatically across different observations. The universe didn't wake up all at once. It flickered to life street by street, leaving its loneliest corners for last. The cosmic web's role might even solve one of reionization's stickiest puzzles: how enough photons escape to ionize the entire universe. Filaments funneled radiation efficiently, preventing it from being wasted on already ionized gas. Voids, meanwhile, delayed the process just enough to let galaxies grow brighter, their later bursts of light finishing the job. It's a story of structure and chaos, highways and dead ends, a reminder that the universe doesn't do simple. Even its greatest revolutions move to the beat of hidden geometry. Ultraviolet light should have been reionization's greatest weapon, a torrent of high-energy photons blasting hydrogen atoms apart. But there's a catch: most of it never made it out of the galaxies where it was born. The problem, known as the UV escape fraction, reveals a cosmic irony. The very gas clouds that fueled star formation also trapped their light, turning early galaxies into gilded cages. If only a trickle of radiation escaped, how did enough photons accumulate to ionize the entire universe? Picture a star blazing at the heart of a dense, primordial galaxy. Its ultraviolet light doesn't stream freely into space, it slams into the surrounding hydrogen, ionizing atoms on contact. Each absorbed photon knocks an electron loose, but that electron soon recombines with another atom, emitting a new photon in a random direction. The result, a game of pinball where light bounces endlessly through the gas, losing energy until it's too weak to escape. For many early galaxies, simulations suggest less than 10% of their UV radiation broke free. The rest churned inward, trapped by the very material that birthed it. So how did any photons escape at all? The answer lies in the cracks, turbulent channels where supernova or stellar winds carved temporary gaps in the gas. Like prisoners tunneling out of a fortress, UV light seized these fleeting exits, slipping through before the hole sealed shut. Some galaxies might have been leakier than others, their gas distributed in clumps rather than smooth cocoons, creating porous escape routes. Others could have hosted hyperactive black holes whose jets punch through the gas, creating permanent chimneys for radiation. The James Webb Space Telescope has spotted clues to this uneven struggle. Some early galaxies show bizarrely strong emission lines from ionized gas, suggesting frantic, last-ditch escapes for UV photons moments before absorption. Others exhibit strange fluctuations in brightness, as if flickering between opacity and transparency like a malfunctioning lighthouse, the most telling detail. Galaxies with the highest star formation rates often show the lowest escape fractions, their furious starbirth buried under thicker gas blankets, paradoxically stifling their contribution to reionization. Yet somehow the universe got its light. One theory points to dwarf galaxies small enough that their shallower gravity wells let gas disperse more easily, allowing UV photons to slip away. Another suggests that the earliest stars formed in sparse, isolated clumps, their radiation escaping before later generations of stars drowned them in gas. The wildest possibility, dark matter again. If certain interactions heated galactic gas from within, it could have thinned the barriers trapping UV light, turning sluggish trickles into floods. The UV escape fraction isn't just a technicality, it's the bottleneck that nearly stalled cosmic dawn. Solving it means understanding why some galaxies became radiant beacons, while others smothered their own light, and how the universe threaded the needle between creation and confinement. Every photon that escaped was a minor miracle, and their cumulative brilliance lit up the cosmos. The cosmic microwave background isn't just a snapshot of the infant universe, it's a scrambled message, imprinted with secrets of everything that came after. Hidden within its faint glow are polarization patterns, tiny directional ripples that act like cosmic fingerprints, recording how and when the first starlight tore through the primordial fog. These patterns split into two types: E modes, gentle swirls tracing density variations from the Big Bang, and B modes, twisted curls that could signal gravitational waves or, crucially, the turbulence of reionization. Together they form the universe's oldest detective story, and the plot twists are far from over. E modes tell the cleaner tale. As the first starlight ionized hydrogen, freed electrons scattered CMB photons, imprinting a new polarization signal onto the ancient light. The strength of this signal, measured as an optical depth tau, should reveal reionization's midpoint. Think of it as a time stamp in the cosmic record. But when the Planck satellite delivered its tau value, it sparked chaos. The data suggested reionization began earlier and lasted longer than simulations predicted, as if the universe flickered awake in fits and starts rather than a single dawn. Some regions might have ionized at redshift 20, while others clung to darkness until redshift 6. B modes deepen the mystery. While primordial gravitational waves could create them, so could the violent scattering of CMB photons during reionization. The problem: no one's sure which signal dominates. If reionization's turbulence left stronger B modes than expected, it could mean the process was far patchier and more chaotic than we've assumed, like a stormy sea rather than a rising tide. Alternatively, it might hint at exotic physics, like dark matter interactions heating the early universe unevenly. The debate rages because tau isn't just a number, it's a cosmic stopwatch. A high tau implies an extended reionization era, with galaxies laboring for hundreds of millions of years to clear the fog. A low tau suggests a quicker, more decisive transition, as if something, perhaps quasars or an early population of massive stars, turbocharged the process. Planck's middle ground value satisfied no one, leaving theorists scrambling to reconcile it with other clues, like the Lyman-alpha forest's patchiness or the James Webb Space Telescope sightings of surprisingly mature early galaxies. The truth might lie in the gaps between E and B. If future telescopes can untangle their signals, we may finally decode whether reionization was a single revolution or a series of scattered uprisings, and why the cosmos took its sweet time stepping into the light. Deep within the primordial darkness, an invisible army lurked, not stars or galaxies, but countless mini halos of dark matter, each no heavier than a small moon. These gravitational potholes, relics from the universe's first microseconds, should have been cosmic speed bumps for reionization, soaking up ionizing photons like sponges in a desert. Yet simulations suggest something strange: their absence. If they existed, why didn't they stall the universe's great awakening? And if they didn't, what erased them from cosmic history? These mini halos were stealthy troublemakers. Too puny to birth stars, they still hoarded hydrogen gas in their shallow gravitational wells. When the first ultraviolet light blasted through, their gas would have absorbed photons relentlessly, converting that precious energy into heat instead of letting it ionize the wider universe. Think of them as cosmic firebreaks, tiny patches of wet forest slowing a wildfire's spread. One mini halo might not matter, but trillions could have throttled reionization to a crawl. Yet the cosmic timeline doesn't show that slowdown, so where did they go? The answer might lie in an early cosmic purge. Before reionization even began, the faint glow of the cosmic microwave background kept the universe warm, preventing gas from cooling and collapsing into these minuscule halos. But as temperatures dropped, mini halos began forming only to face annihilation when the first stars ignited. Their ultraviolet radiation didn't just ionize hydrogen, it heated gas to furious temperatures, evaporating the fragile hydrogen clouds clinging to dark matter's faintest clumps. It's like blasting a mist with a blowtorch. The droplets vanish before they can impede the flame, yet some models suggest this heating wasn't enough. Mini halos in denser regions might have stubbornly persisted, their gas continually replenished by cosmic filaments. That's where a second killer enters, supernova shockwaves. When the first massive stars died, their explosion sent ripples through intergalactic space, stripping gas from mini halos like leaves in a hurricane. Simulations show these shocks could have sterilized vast regions, leaving behind naked, dark matter clumps, ghosts with no gas left to absorb photons. But here's the twist: the James Webb Space Telescope might have found survivors. Some faint ancient galaxies appear embedded in swarms of even fainter objects, potential mini halos, that clung to a wisp of gas just long enough to leave shadows in quasar light. If confirmed, they'd rewrite reionization's efficiency. Instead of a smooth march, we'd see a brutal battlefield where photons fought through layers of defense, with mini halos as the sacrificial pawns. The deeper mystery, dark matter's true nature. If mini halos were rarer than expected, maybe dark matter isn't cold, but slightly warm, particles zipping fast enough to avoid clumping at the smallest scales. Or perhaps interactions between dark matter and radiation heated these halos from within, sabotaging their gas supply before reionization even began. Either way, their suppression wasn't just a footnote, it was a cosmic coup. By vanishing or being vanquished, these tiny halos let light flow freely, turning what could have been a sluggish slog into the universe's brilliant rebirth. Their absence isn't a gap in the story, it's the reason the story had a happy ending. X-rays might have been the universe's secret weapon during reionization, not by directly ionizing hydrogen, but by preheating gas in a way that made it surrender its electrons more easily. Picture a blacksmith softening metal before shaping it. Early black holes and stellar remnants could have flooded the cosmos with X-rays, warming hydrogen just enough to loosen its grip on electrons, setting the stage for ultraviolet light to finish the job. This preheating theory offers an elegant solution to one of reionization's biggest puzzles: how photons overcame the universe's stubborn neutrality. But the evidence isn't so cooperative. Some observations suggest X-ray heating arrived fashionably late, missing the party when it was needed most. The logic behind X-ray preheating is simple yet profound. While ultraviolet photons from stars and quasars carried the energy needed to ionize hydrogen, they struggled to penetrate dense gas clouds. X-rays, though less efficient at ionizing, could travel vast distances before being absorbed, depositing heat wherever they went. Warm hydrogen resists recombination, the process where electrons snap back onto atoms, meaning, once X-rays raised the gas temperature, it stayed ionized longer, reducing the workload for ultraviolet light. Think of it as a cosmic warm-up act, transforming the primordial fog into a more pliable state before the main event, yet the timing of this heating spree is wildly contentious. Studies of the cosmic microwave background's polarization hint that gas temperatures didn't rise uniformly until well after reionization began. Meanwhile, the Lyman-alpha forest, those absorption lines in quasar light, shows pockets of gas that remained eerily cool, as if X-rays skipped entire neighborhoods. If X-rays were the universal softeners, why do some regions appear untouched? The James Webb Space Telescope adds another wrinkle. Its observations of early galaxies reveal intense X-ray activity near supermassive black holes, but these sources seem clustered in certain eras, leaving gaps in the timeline. One explanation: early X-rays might have come from microquasars or accreting stellar mass black holes, smaller, dimmer sources that heated gas locally rather than globally. This would create a patchwork of preheated zones, explaining why some gas ionized effortlessly while other regions lagged. The wild card here is dark matter. Some theories suggest decaying or annihilating dark matter particles could have produced X-rays, injecting heat long before the first black holes awoke. If true, this would rewrite the preheating narrative entirely, painting dark matter as the invisible hand that primed the universe for reionization. For now, the X-ray wildcard remains unresolved, a tantalizing what-if lurking in the data. Whether it was a dominant force or a bit player, one thing's clear: the universe's path to light was far messier and far more creative than we ever imagined. What if reionization wasn't one cosmic event, but two? The double reionization hypothesis is astronomy's most tantalizing curveball, suggesting the universe didn't simply awaken from darkness. Instead, it flickered, stumbled, and reignited like a faulty neon sign. The evidence: helium specifically, its stubborn refusal to follow hydrogen's timeline. While hydrogen reionization dominates discussions, helium tells a messier story. Observations of distant quasars reveal something bizarre: helium's second ionization, when it lost its last remaining electron, didn't smoothly follow hydrogen's lead. Some patches of intergalactic helium appear ionized shockingly early, as if scorched by an initial wave of radiation, while others lingered in neutrality for hundreds of millions of years longer. This staggered timeline has led some theorists to propose a radical rewrite. Reionization didn't unfold as a single rising tide. It surged, retreated, and surged again, a cosmic hiccup with profound implications. The first wave might have been sparked by population 3 stars, those primordial giants born in metal-free nurseries. Their blistering ultraviolet radiation could have ionized hydrogen, and even some helium in localized bursts. But these stars were short-lived, and as they died, their ionizing light faded. Without sustained energy input, the universe's expansion diluted gas densities, allowing electrons to recombine with atoms. Neutrality crept back in like fog rolling over extinguished streetlights. Then came the second act: quasars. When supermassive black holes awoke in galactic cores, their X-rays and ultraviolet fury reignited the stalled process. This time the radiation was more penetrating, more relentless. Quasars didn't just reionize hydrogen, they finished what the first stars started, stripping helium's last electrons in a late-breaking inferno. The smoking gun: quasar absorption spectra show helium's final ionization coincides with their peak activity around redshift 3, long after hydrogen's fog had lifted. Critics counter that this two-phase model overcomplicates things. If the first wave was so fleeting, why do some Lyman-alpha forest measurements suggest continuous ionization? Others argue that patchy helium could simply reflect uneven quasar distribution rather than separate epochs, but Webb telescope observations are muddying the waters further. Deep field images reveal galaxies with shockingly mature stellar populations at redshifts that shouldn't exist if reionization were a single, smooth event. The stakes here are cosmic. If double reionization is real, it means the universe's great awakening was halting, fragile, a near miss where darkness almost reclaimed dominance. It suggests that light's victory wasn't inevitable, but a staggered triumph, won against improbable odds. And if we're reading those helium signals right, we might need to rewrite the entire story of how our cosmos came to shine. Stellar archaeology might sound like science fiction, but it's happening right now, inside our own cosmic backyard. The Milky Way's oldest stars are more than luminous relics, they're frozen artifacts from the Cosmic Reionization Era, their chemical compositions etched with secrets about how light first conquered the universe. Unlike distant galaxies, these ancient survivors are close enough to dissect atom by atom, offering a front-row seat to the chaos of cosmic dawn, their most revealing feature. A near-total lack of metals elements heavier than hydrogen and helium, making them pristine witnesses to the era when starlight was still a novelty. Take the star HD 140283, one of the oldest known in our galaxy. Its atmosphere contains barely a trace of iron, yet it harbors unexpected bounties of carbon and oxygen. This bizarre cocktail suggests it formed from gas polluted by the very first supernova explosions so violent, they forged elements in ways modern stars never replicate. These anomalies are cosmic breadcrumbs, hinting at how reionization's ultraviolet flood altered the chemistry of star-forming gas. When UV light ionized hydrogen, it also heated it, changing how metals mix through primordial clouds. Stars born during this turbulence locked those conditions into their atmospheres like celestial time capsules, but the real breakthrough comes from comparing these fossils across the local group, our galactic neighborhood. The Small Magellanic Cloud, a satellite galaxy of the Milky Way, hosts ancient stars with even fewer metals than our oldest, suggesting it experienced reionization later or less intensely. Meanwhile, in the Andromeda Galaxy, some metal-poor stars show unusual bursts of heavy elements, as if their birth clouds were showered with debris from multiple supernovae in quick succession. This patchwork of chemical signatures paints a startling picture. Reionization didn't just light up the universe, it reshaped the very ingredients of star formation, from region to region. The smoking gun lies in lithium. This fragile element gets destroyed easily in hot gas, yet the oldest stars preserve more of it than modern models predict. One explanation, reionization's UV radiation might have suppressed cosmic rays, which typically break lithium apart. If confirmed, this tiny discrepancy could reveal how radiation fields fluctuated during the universe's awakening, offering clues about the timing and intensity of ionization in our corner of space. Yet these stellar fossils come with riddles of their own. Why do some show pockets of heavy elements amid otherwise pristine gas? Could early supernova have peppered the cosmos with metal-rich pockets like cosmic shrapnel? Or did reionization itself stir the primordial soup, creating uneven pockets of pollution? Each anomaly forces us to rethink how light and matter intertwine during this chaotic epoch. The answers aren't just locked in distant quasars or fading radio signals, they're shining overhead, in stars that watch the universe's first sunrise. Point your telescope at one patch of sky, and the story of reionization seems clear: galaxies blazing to life in a steady march toward cosmic dawn. Swing it slightly to the left, however, and the narrative unravels, with conflicting signals suggesting a universe that woke up earlier, later, or in disjointed fits and starts. This frustrating inconsistency isn't a flaw in our instruments, it's a fundamental property of the cosmos called cosmic variance, and it's forcing astronomers to confront an uncomfortable truth: we might be missing the forest for a few scattered trees. The problem stems from reionization's patchwork nature. Ionization didn't sweep uniformly across the universe, it propagated through a labyrinth of galaxies, quasars, and gas clouds, each region following its own timeline. When we observe deep fields like the Hubble Ultra Deep Field or Webb's first deep field, we're essentially peeking through tiny keyholes fractions of a degree wide into a cosmos that was wildly uneven on vast scales. Imagine trying to reconstruct Earth's climate history by sampling a single square mile of the Amazon rainforest, the Sahara, and Antarctica. You'd get three radically different stories. Cosmic variance means that even with perfect data, small survey areas can't capture the full chaos of reionization's rollout. the James Webb Space Telescope has magnified this dilemma. Its early deep field images revealed galaxies at redshift 10 and beyond, some appearing suspiciously mature for their age, but were these objects typical pioneers or cosmic outliers, bright freaks in an otherwise dim landscape? Without surveying wider swaths of sky, there's no way to know. This isn't just academic quibbling. If one field shows galaxies ionizing their surroundings by redshift 12, while another suggests a slower process ending at redshift 6, our entire timeline of cosmic dawn could be skewed by statistical noise. Cosmic variance doesn't just obscure the when of reionization, it warps the how. Case in point, early Webb observations found a handful of galaxies with ionized bubbles far larger than simulations predicted. Were these bubbles carved by supermassive black holes, ultra-efficient starbursts, or some unknown phenomenon? The answer might depend entirely on whether such galaxies were common or one-in-a-million flukes. Without broader surveys, we're left guessing whether these objects were central players in reionization or mere spectators. The solution: quantity over precision for now. Astronomers are trading ultra-deep but narrow fields for wider, shallower surveys, sacrificing razor-sharp detail for statistical muscle. Projects like Webb's Cosmos Web aim to map an area 50 times larger than the original deep fields, stitching together a mosaic where cosmic variance smooths out into recognizable patterns. It's the difference between studying a single lightning strike and tracking an entire thunderstorm. Only by seeing the whole system can we understand its rules. Yet even this approach has limits. Reionization's variance might extend beyond mere geography, with differences in dark matter density, gas composition, or even primordial quantum fluctuations creating regional personalities that resist averaging. Some theorists suggest the universe's first billion years weren't just patchy, they were fractal, with irregularities repeating at every scale. If true, even the widest surveys might only reveal part of the truth. The cosmic variance dilemma is humbling. It reminds us that the universe owes us neither consistency nor convenience, and that the story of light's triumph over darkness may be messier and more magnificent than we ever imagined. Until we gaze upon more of its chapters, some mysteries will stubbornly refuse to come into focus. Active galactic nuclei weren't just cosmic lighthouses during reionization, they were also shadow casters. Whether blazing radiation ionized gas for millions of light years, these monstrous black holes might have simultaneously sculpted vast neutral dead zones in their surroundings, like fire pits ringed by untouched frost. This paradox, the AGN shadow effect, turns our understanding of reionization on its head. Instead of a uniform march toward transparency, the universe could have been a checkerboard of light and dark, where ionized bubbles bordered stubborn neutral patches shaped by the very objects that lit them up. The mechanism mirrors modern-day Stromgren spheres, those hollowed-out regions around hot stars where hydrogen is fully ionized but blown up to cosmic proportions. When an AGN flares to life, its radiation carves a nearly perfect sphere of ionized gas. But here's the twist: at a critical distance, the radiation's intensity drops sharply, creating a razor-thin transition zone where hydrogen flips from fully ionized to completely neutral. Beyond this edge, the gas remains untouched, not because the light is blocked, but because the photons have stretched to wavelengths too weak to strip electrons. It's like holding a lighter to a sheet of ice close enough, it melts a hole. A few inches back, the ice stays frozen despite the flame. These shadows wouldn't have been static. As AGN flickered on and off, their brightness swinging by orders of magnitude over millennia, their shadows pulsed outward and inward like a lung breathing in reverse. During quiet phases, neutral gas could creep back toward the black hole, only to be blasted away again at the next outburst. This stuttering rhythm might explain some of the Lyman-alpha forest's strangest features: alternating bands of ionized and neutral hydrogen in quasar light, like tree rings recording the AGN's life cycle. The James Webb Space Telescope has spotted potential shadows in the wild, One distant galaxy, observed just 800 million years after the Big Bang, shows a bizarrely sharp cutoff in ionization at its outskirts, too abrupt for typical star-driven reionization. Another reveals a Swiss cheese pattern, bubbles of ionized gas peppered with neutral clumps that align perfectly with the locations of smaller AGN nearby. These aren't random holdouts, they're shadows in the truest sense, their shapes dictated by the geometry of radiation fields from multiple black holes. Yet the AGN shadow effect raises thorny questions. Why don't all AGN show these features? Some quasars appear to have ionized their surroundings uniformly, leaving no neutral borders. The answer might lie in gas density. Shadows form best in low-density regions where radiation drops off steeply, while denser gas smooths the transition, blurring the shadow's edge. It's the difference between shining a flashlight in open air where the beam's edge is crisp versus fog where light diffuses. Another wrinkle, magnetic fields. If early galaxies wound their magnetic fields into tight coils around AGN, these invisible lines could have funneled ionizing radiation into jets, leaving vast wedges of neutral gas untouched between them. Imagine sunlight streaming through slatted blinds, bright stripes alternating with dark only on galactic scales. The implications rewrite reionization's playbook. If AGN shadows were common, they'd create a universe where ionization advanced not as a steady tide, but as a fractal network of light and dark, with neutral hydrogen surviving in sprawling filaments between ionized bubbles. These shadows might even have sheltered pockets of pristine gas, delaying star formation in some regions while accelerating it in others. Far from being mere bystanders, AGN could have been cosmic sculptors, chiseling the universe into a mosaic of transparency and opacity whose echoes linger today. The 21-centimeter signal from the early universe should have been a straightforward cosmic broadcast, a clean transmission revealing how hydrogen atoms behaved during reionization. But when astronomers finally tuned in, they discovered a bizarre anomaly: hydrogen's spin temperature, the property dictating how these atoms absorb and emit radio waves, wasn't behaving as predicted. Instead of a uniform background hum, the data revealed wild fluctuations, as if the universe had turned its volume knob up and down at random. This spin temperature enigma isn't just a technical hiccup, it's a glaring clue that we're missing something fundamental about how light and matter interacted in the cosmic dawn. Spin temperature hinges on a delicate quantum dance. Hydrogen atoms can exist in one of two hyperfine states: parallel or antiparallel proton and electron spins separated by a whisper of energy. When these atoms absorb or emit 21-centimeter photons, they flip between these states, creating the signal we detect. The catch: this dance depends on three competing influences: collisions between atoms, interactions with the cosmic microwave background, and here's the wildcard: Lyman-alpha photons from the first stars. Normally, theorists assumed collisions dominated early on, coupling the spin temperature to the gas's kinetic temperature and making the 21-centimeter signal a straightforward cosmic thermometer. But the real universe loves chaos. Enter Lyman-alpha pumping, the process that appended the models. When ultraviolet light from early stars redshifted into Lyman-alpha wavelengths, it bathed hydrogen atoms in a flood of photons capable of flipping their spins through something called the Wouthausen field effect. This wasn't just background noise, it was a cosmic control knob, yanking spin temperature away from the gas's kinetic temperature and locking it to the radiation field instead. The result: regions bathed in Lyman-alpha light could show 21-centimeter absorption or emission wildly out of sync with their actual thermal conditions, like a faulty thermostat stuck on high despite a freezing room. The anomalies don't stop there. Some areas of the early universe appear to have spin temperatures colder than the cosmic microwave background, impossible without some exotic cooling mechanism. Others flicker between absorption and emission in ways that suggest Lyman-alpha photons weren't arriving steadily but in erratic bursts, as if the first stars flickered like candle flames in a drafty cave. The EDGE's experiment's detection of an anomalously deep 21-centimeter absorption trough only deepened the puzzle, hinting at gas colder than standard physics allows. Could dark matter have siphoned energy from hydrogen, or did cosmic rays from the first supernova scramble spin states in ways we haven't accounted for? The James Webb Space Telescope offers a tantalizing lead. Its observations of early galaxies reveal Lyman-alpha photons escaping earlier and in greater quantities than simulations predicted, suggesting the first stars might have pumped hydrogen's spin temperature into chaos sooner than anyone guessed. Meanwhile, radio arrays like Hera and the Square Kilometre Array are hunting for the spatial patterns behind these anomalies. If spin temperature fluctuations align with galaxy clusters or cosmic web filaments, it could mean Lyman-alpha's influence was sculpted by large-scale structure, a hidden hand guiding reionization's uneven march. The spin temperature mystery isn't just about fixing a glitch in the models, it's a window into the untamed physics of the cosmic dawn, where light didn't just illuminate the universe, it rewrote the rules. Until we crack this code, our picture of reionization remains half static, like a radio stuck between stations, straining to hear the song beneath the noise. The universe was declared fully reionized roughly 1 billion years after the Big Bang, a cosmic graduation from murky darkness to luminous clarity, yet scattered across the cosmos, stubborn holdouts remained fossil clouds of neutral hydrogen that somehow resisted the flood of ionizing radiation for billions of years longer. These cosmic stragglers, making up less than 1% of the universe's hydrogen, shouldn't exist according to our cleanest models. If reionization was as thorough as we believe, how did these pockets cling to their electrons against all odds? One possibility lies in the voids, those desolate regions between the filaments of the cosmic web where galaxies are sparse and intergalactic gas stretches thin. Here the rules of reionization bent. With fewer stars and quasars to blast ultraviolet light, these vast, near-empty regions became ionization's final frontiers. Radiation struggled to penetrate their depths, like sunlight fading in the ocean's abyss. Worse, the gas here was so diffuse that even when photons did arrive, they often passed through without encountering a single hydrogen atom to ionize. It's a cosmic game of needle in a haystack, except the needles are photons, and the haystack is a million light-year wide vacuum, but isolation alone doesn't explain everything. Some neutral hydrogen survived in plain sight, lingering near bright galaxies that should have sterilized their surroundings. This paradox hints at something stranger: absorption camouflage. Imagine these hydrogen clouds as cosmic chameleons, armored with dense layers of dust or molecules that absorbed ionizing photons before they could reach the gas. Or perhaps magnetic fields, twisted into protective cages, trap the hydrogen in a feedback loop, each ionization attempt generating currents that reinforce the fields, creating an impenetrable shield. The James Webb Space Telescope has spotted candidate systems, galaxies cloaked in neutral halos that flicker in and out of transparency as if flicking a cosmic dimmer switch. The wildest theory: these holdouts might be time capsules, regions where the physics of the early universe never ended. Quantum fluctuations from inflation could have left behind ultra-dense knots of gas, frozen in a pre-reionization state. Alternatively, dark matter's gravity might have corralled hydrogen into deep wells, sheltering it like artifacts sealed in a cosmic vault. The truth is, we've only begun to catalog these outliers. Each one is a rebel against the universe's march toward light, and their defiance might rewrite the story of how darkness finally fell. What began as 25 isolated riddles now reveals itself as a grand cosmic tapestry, each thread intertwined with the next, pulling the story of reionization into focus while weaving new gaps in our understanding. The trigger of reionization isn't just about pinpointing the first stars or quasars, it's about the chaotic collaboration between galaxies, dark matter, and forces we've yet to name. The timeline's contradictions, where some regions flickered to life while others clung to darkness, aren't inconsistencies, but clues to a universe that woke up in patches, its ionization as uneven as the galaxies that drove it. And those missing dwarf galaxies, their absence isn't a census error, it's a revolution, forcing us to question whether dark matter's rules were different in the dawn of time. The Lyman-alpha forest's tangled absorption lines, the spin temperature anomalies, the ghostly whispers of population, 3 stars, these aren't just puzzles. They're pieces of a singular mystery, how light carved its path through a resistant cosmos. Even the cosmic web, with its filaments and voids, wasn't just a backdrop, it was the highway system that shaped reionization's advance, while helium's silent second act proved the universe's transformation wasn't a single event but a layered upheaval. And those X-rays, they might have been the unsung prelude, softening the universe for the ultraviolet onslaught to come, yet the most profound lesson lies in the contradictions. AGN cast shadows even as they illuminated, many halos vanished without a trace, their absence as telling as their presence would have been. Metal pollution, instead of stifling star formation, accelerated it in a paradox that defies intuition. Every anomaly, from the 21-centimeter signal's eerie silence to the fossil clouds of neutral hydrogen that outlasted their peers', challenges us to rethink not just reionization, but the fundamental laws that govern our cosmos. This is more than astronomy, it's a mirror held up to our origins, the atoms in your hands, the light in your eyes, the very fact that you exist to ponder these questions, all trace back to this epoch of chaos and rebirth. Solving these mysteries isn't just about filling textbooks, it's about rewriting the story of how we came to be, one enigma at a time. So which mystery pulls at your curiosity? The quasars that flickered too briefly, the dark matter halos that sculpted galaxies from the shadows, or the cosmic variance that reminds us how much of the universe's story remains hidden? Drop your thoughts below, let's geek out over the cosmos together, and if you're hungry for more deep dives into the universe's greatest riddles, hit subscribe. The next cosmic revelation is always just past the event horizon.